Okay. I don't want to see this. So let's just reduce it somehow. And let's get back to Zoom. Now, where's my sharing option? I don't want to see this. So let's just reduce it somehow. I have to hear it. Okay. And let's get back to Zoom. Now, where's my sharing option? Okay. So I'm sharing and I'm live streaming and it's hearing. I need to stop hearing it. I'm sharing and I'm live streaming. This is the YouTube. So can I just close it and still be live streaming? Okay. Am I live streaming? I don't know. I think that means I'm live streaming. I don't know. You're sharing screen. I'm sharing that screen. Okay. Kara, can you give me a thumbs up if you can still see the screen? Thank you. All right. So I think I'm recording. I think I'm recording to my YouTube account. What the hell? Okay. Let's see what we're doing today. Okay. So today I have to go over homework 3. And look at the classwork stuff and go over questions. But I think what I'm going to do for homework 3 is look at quiz 3 first. So let's take a look at quiz 3. There aren't a lot of questions here from quiz 3 that you guys didn't get. But okay, let's take a look at this one. Just use this Desmos link to find. Okay, so do y'all see this? Let me make it bigger. All this is they want you to evaluate the function in 3.5. They want what? What does that little prime mean? What does the little prime there with the F mean? Yes, and what does the 2 primes mean? 2 derivatives. So if we click on this link, and we want 3.5, right? That's our numbers. We go here, there's some data, there's a graph. We scroll down, there's a regression, right? There's the function, and then they want it at 3.5. So I just put in 3.5. Okay, some people do this, and they go over to 3.5, and they give me a number like that. 6. That's fine. That's fine for 3.5. 667.9, or say 668, right? But that's not going to tell you the first derivative or the second derivative. And then some people give me 113 as the first derivative. Where's the second derivative? That's the first derivative. That's 1 primes. I could, or I can just expand it like that. Or let's just say I can do this. That would work too. Okay. I think that's all we have to do for this problem. Oh, where'd it go? Oh, it's here. So the answer is minus 50. Oh, it needs units. Okay, so back to the problem, which is here. You have to look at that. See, so it's months and it's outbreaks. Oh, really? It does, and that's, but then the problem says to use cases per month. So it would be 668 cases, 113 or 114 what? Cases per month. And then it would be minus 50 what? Cases per month. Yep. And that's the answers that are here. Minus 50, 114, and 668. Okay. Any questions on that? Oh, looks like only one person had that problem. And they didn't get it. So, okay. On to the next one. How do you say this? Anyone? Derivative? Derivative of sine is cosine. Okay, so I didn't mention the t, but you could use any variable for that. Okay. Right, one more of these. Okay, Desmos, make the following. According to the blank regression in the third month, there will be blank cases increasing by blank cases per month and decelerating by. Okay, so what do I have to do here? I'm going to click on this Desmos link. And what am I looking for? According to the blank regression, what regression is it? What regression is this? Oh, it doesn't say what regression. But what is it? What's the regression looking at this? Quartic, it's to the fourth power. We're using quartic regression all the time. This isn't pre-calculus, but you have to tell me what regression you're getting it from. And so I use quartic most of the time. Okay, and then it says in the third month, what? How do I get the third month again? Put a 3 in the X column. So it's 600, 167, and minus 150. Do they need units? No, because the units, because it's already given. In the third month, there will be, whatever, 600 cases, and it'll be increasing by 167 cases per month and decelerating by 150. Now, just out of curiosity, with the problem, there's a minus with the 150. If they say decelerating, you don't say decelerating by minus 150, because now you're doing a double negative. The decelerating is because it's negative. If it were positive, they would use what? They would say what? Accelerating. Yes. Okay, any questions on that? Was this quiz hard? Because it looks like everybody got everything on, like those were the 3 questions people missed. And by the way, that doesn't look like, it's very possible that 3 people just skipped those questions. Okay. All right, everybody else got hundreds on it, so it wasn't that bad. All right. Tells me, how's the average score 11.5 and the amount of time it took was 1 minute? Couldn't have been that fast. Something's not right here. Oh well, whatever. Any questions on this before I close it up? Going once, going twice, anyone from home? We're good. All right, it's gone. And let me get rid of these 2. So these ones that come from the discussions, they're pretty easy. Yes. The questions that people miss the most are the third question, the reading and tell me what happened here questions. Those ones people miss. Okay, so let's look at the next thing, which is last week's discussions here. These are due tonight, right? And these are the derivatives are due tonight, or were they due last week?
Tonight.
Due tonight. Did you finish them?
So.
Okay. Let's start with Davon's group. Davon, you're here. How come you didn't want to be at home? Too much. No, it's fine. I see you're all rewarding me by sitting all over there. So I will catch your COVID. Okay, all right, so Devon, you put the link here. That's very nice. And this is your post. And then you have the function, the first derivative, second derivative at 5 and at 20. Okay. So Lila said, oh, Nana said it. Can I play this? Nana, can I play it? You want to just say it? Did you not say it right? Let me just play it.
95 equals 70.5%.
Yes.
F prime of 5 equals 7.0% per hour studied.
Yes.
F double prime of 5 equals 0.08% per hour studied per hour.
Perfect. Why would you not want me to play that? It's perfect. Okay. And Melanie said this. Melanie's here. So, but Nana, you read this? Did you just read it exactly as it says here? Let's see. It's saying nothing. Is it saying something and I can't hear it? Or is it? Okay, so it's not working. You'll still get credit, don't worry about it. But you want to read this for me? Can you read it? You don't want to read it? Okay. Yes, now I know why I have to play the recording, because people at home probably couldn't hear you. Do you hear her? No, it's okay. No, it's good because now I know why I have to have these recordings, which works out great. Because if you say it in class, they may not hear you. Okay, super. Good. Fine. You don't have to be recorded. All right. Next post, Sarah. Sarah is talking about this is the same thing, Sarah. Are you in her group?
There's a lot of people in there.
Oh. So did you just do a second? Okay, so Jacob just picked a different, he just picked 9. And Sarah, you okay. All right. After 9 hours of studying, we'll receive a 60%. For every study up that you'll gain 5.9%. Your grade will decelerate by 0.53% per hour studied per hour. What is striking me as odd here? Okay, it's not for every hour. So let me just talk to you about the derivative. The derivative is the instantaneous rate of change. It's good there. And so at 9 hours, you're going to pick up, you're getting a 60. Okay, so 9 hours is like the beginning of passing. Then for the next hour, you'll pick up 6%. So between 9 hours and 10 hours, you should pick up about 6%. Okay? But now you will be at 10 hours. And 10 hours might have a different derivative. Okay, so you can still say $9 per or 6, you can still say 6% per hour. But it's just there. And you can estimate afterwards, but this, because it's accelerating or decelerating, it won't be as big as 6. It's 5.9, it'll be less. That's what decelerating means. It's not staying if it weren't accelerating or decelerating, then it would be 6 again the next hour. But since it's decelerating at 10, you're not going to pick up 6%. Does everyone understand that? So you studied 9 hours. And you figure if I study another hour, I'll pick 6%. I'll get to passing. I'll get to 66%. Woohoo! Okay, and that may be true. But then if you do another hour, you're not going to get to 72. You'll get to something a little less than 72 because it's decelerating. Okay, let's see if that looks this from the graph, if you can see that. So,
Like.
no, you just leave it, it's fine. It's just, I just want you to understand that it's not every hour after that. It's just the next hour after that. It's changing by 6% per hour. That's because remember, it's an instantaneous rate of change. It's just at that instant. It really isn't even true at 6.1 hours. Once you've studied for like 10 minutes, it's not, there's no guarantee you're going to pick up 6%. This is just the rate and it's how quickly it's changing there. This used to bother me because I thought, well, if you're gaining 6 an hour, then you should gain 6. It's like, no, not if you're decelerating. You start up at 6 hours. Like if you think you're going to, suppose you're going 6 miles an hour from here to home, and you know home is an hour away, right? Let's just say that it's not an hour away, but let's just say if you're going 6 miles an hour and your home is 6 miles away, let's say it that way, and it's going to take you an hour at 6 miles an hour. So you get in your car and you're going 6 miles an hour, but you start decelerating. What are you doing? You're slowing down. Are you going to make it home in an hour? No. It depends on how fast you're going all along. Like if you just keep slowing down and you brake after 5 minutes, you didn't make it home. Okay? So the rate that you're going is not the same as how much you're accomplishing. Like if you're like 60 miles an hour is only good if you're doing it for a whole hour. Then you went 60 miles. 6 miles, 6% an hour is only good if you study for a whole hour. And it stays relatively constant. If you decelerate in that time, then you can't even guarantee you're going to get to 66%. Okay? Are we good? Karen, good? Thumbs up. Thank you for leaving your video on because I can see your face. Okay. Anybody else? Anything else? So we have one more to do, right? Hold on. We're going to spend more time studying what the graph looks like with this when it's accelerating and decelerating because that's called curve. We'll do that later on. Anusha, you are here, yes?
Yes, hi.
Hi, Anusha. And hold on. You're doing salary and BFFs, right?
Mm-hmm.
Okay. And so you have at 15,000, a person has a lot of BFFs and it's going down, but it's accelerating. At 150, they have hardly any friends. It's still going down. And it's decelerating, not accelerating. So let's see what Kara says. Kara, you don't have to say anything. She's at 15. You have at $15,000. So be careful though. Okay, this is $1,000. All right. So it's at $15,000. You have 12 friends. You're losing almost you're losing 7/10 of a best friend for every $1,000 at that point. Okay. And it is accelerating. Okay. And Mahir said that is Mahir here. Okay. When you're saying things, this is what I wanted you to fix, Sarah, on yours. Don't say 11.57. Don't, if this is for your mom, just say 12. And for minus 0.69, you could say minus 0.7. And decelerating by 0.02 of a best friend, that I wouldn't even say by 0.02, I'd say by hardly any. It's decelerating by a very small amount because again, mom doesn't care what what is 0.02 of a best friend? Not to mention this is wrong because it's best friend per $1,000 per what? How do we do the accelerating and decelerating? Remember, one is BFFs. Oh, this is wrong in a lot of ways. It's not 15 BFFs, it's 15 what? Karen's the only one here and she doesn't want to answer. Anusha, what's the x-axis? Thousands of dollars. So why is me here saying at 15 BFFs? It's $15,000, right? He'll have how many? What's this then? How many? All right, let's see if Suhabi said it. If Suhabi, did you say what Mahir said? Because if you said what he wrote, you're wrong.
Yeah, I read it. I read it as it was.
Okay, so you want to correct it,
Okay.
but read it. Tell me what you would say. If you don't read it out loud right now, because just read it out loud, but change things if you can.
Okay. So according to the Cortic regression, is it, yeah, 15, is it 15,000 and then BFFs?
A salary of $15,000.
Yeah. And then
Me-
the 11.57 or the 12 is the BFFs
12 BFFs
with negative 70. Is that still, yeah, negative 0.7 BFFs per $1,000 and deaccelerating by 0.02 BFFs per $1,000.
per, say it again.
Okay, so when I re-record
No,
it,
no, not the whole thing. At the end, where it says per $1,000, you have to say per $1,000 what? Per $1,000,
Per-
let's say twice.
per $1,000 per $1,000.
Yes, that's what
Okay.
accelerating does. Accelerating, just like this is
Yeah.
best friends per $1,000. If it's decelerating, it's per $1,000 per thousand. It's best friends per $1,000 per $1,000.
Okay,
So
so should I re-record it with the right terminology?
if you could, that would be
Okay.
great. And Mihir could fix his, or he's gonna lose points because it's not making any sense the way it is. Okay, any questions? I think that's all my posts. Okay. Do we understand what we're talking about? When we're talking about derivatives, the evaluating function and derivative and second derivative. I think next time you have transcendentals. Is that the next discussion we're working on starting today? Transcendentals and the mean value theorem. I'm not sure which one's next though. I feel like transcendentals is next. All right, but we've done the mean values. The transcendentals will go pretty quickly, and then that mean value theorem we did last time. All right, so I want to talk to you today about, I'm going to do my class questions in a little bit, but the topics we have to cover this week are something called implicit differentiation. Okay, so this is an application of derivatives. It's not really an application derivative. So we've been taking derivatives of functions, right? And a function, when you say f of x equals, that's called explicit. When I say f of x equals x squared, that's explicit. Implicit is when the function's implied, but it's not given to you exactly. So my mom used to say, when we did something bad, she'd say, heads are going to roll. What was she implying by that? What? Yeah, more than that. Getting in trouble is sort of implying like something bad is going to happen. Yes. What do you think she meant? You know what she actually meant? It took me a long time to figure this out. Do you know the French used to cut off people's heads with a guillotine and then they'd roll in a basket? That's what my mom meant. She's like, heads are going to roll. Is that she's gonna chop off heads. She wasn't gonna do that, but that would be explicit. If she says, I'm gonna chop off your head and roll it into a basket, that's explicit. That's exactly what's going to happen. But heads are gonna roll is just implied. Do you understand the difference between implied? So what's happening with implied is we're gonna have equations with functions in them. And then we're gonna use just the regular rules of derivatives. Implicit differentiation isn't so bad. Okay. The next thing we're going to talk about is hyperbolic. So this is a whole category of functions. These are called hyperbolic trig functions, hyperbolic sine, hyperbolic tangent. These are all new functions. They really could have been taught in pre-calculus, but I guess you had too much to do there, so they put it here. So it's just another function, and we're going to have to, so it's another transcendental function, and honestly have not, other than in Calc 3, I've never seen them used anywhere. Except, have you ever heard of the Louisiana? In Louisiana, there's a St. Louis Arch. Anyone heard of that? St. Louis Arch? Let me Google it. No one's ever heard, anyone online heard of the St. Louis Arch? No. It's a famous arch. It's a famous monument. It looks like look, it's tall. Images. It looks like this. No. Yes. No. Honestly, I've never been to St. Louis. I have a student that lives there. But anyway, it's an arch. Anyway, that's not a parabola. It doesn't fit a parabola. It fits one of these hyperbolic functions. So we'll learn about them, but there's not much use for them. Unless you're taking Calc 3. What happened to my notes? Here we go. Newton's method is, so I love Newton's method because Newton's method allows you to get more decimal places. But I don't know if you noticed, but the last time we were on Desmos, the company that owns Desmos, remember, Desmos is free to you. It's, I don't know who makes it, but it's some company that makes money, gets grant money, and they make it free to everybody. And that's their goal, is just offer this service free. And it's awesome because you don't have to buy a calculator now. Those calculators are expensive. But when you ask to solve an equation or whatever, it only gives you 3 decimal places. So Newton's method is an application of derivatives that will allow you to get 6 decimal places or more, which would be great if you work for NASA or something. But someday, Desmos will give you 6 decimal places. Just be able to say, give me more decimal places, and it'll do it. And then Newton's method will be worthless. So while I love Newton's method, and while it's fun and relevant now, I have to let go of it. It's not, as I say, your future. It's not going to sell you anything in the future. You're going to be dumbfounded when someone says, what can you do with the Newton's method? You'll say, I don't know why I wasted my time on that. Okay, and then the last thing we're going to talk about is higher order derivatives. So that's second derivatives, third derivatives, fourth derivatives, and so on. Okay, so we're going to have to be able to say them out loud. So the speaking out loud part that you're going to need from here is how to say higher order derivatives. And also the hyperbolic trig functions have special things I have to say. Okay, unfortunately, I don't have that ready today, so we can't say them. So I'm just going to go with my notes. Let's see what we got for notes. And anything else? So everything that's due today, we're good that it's the derivatives is due and quiz 3 is due. All right. St. Louis Arch, because you're not interested in it. Let me get my notes out. Lessons. Oh, so let me start off with mod 4. Oh, it's the hidden from students. I'm so sorry. I did not unhide it from you. That's terrible. Okay, so hold on. Let me just do this. Make available. So now when I click on mod 4, I got to give you a moment here. These are the class questions I'm going to ask you. Suhabe gets what is calculus?
This.
Oh, go ahead.
Sorry, the study of change.
Okay, very good. So that's what we're doing here, right? Very good. Let me see, who else do I have here? Going down, going down, going down. Nyla. What are the other ways of saying IRC? What does, we'll say IRC, what does that mean? Instantaneous rate of change, and what are the other ways of saying it? Derivative, slope of the tangent line, dy dx. Okay. Everyone good with that? That's all of those mean instantaneous rate of change. Okay, Sarah, what's the derivative of a constant? Oh, hard one. Okay, Jacob. What's the derivative of x to the nth power? X to the n minus 1. Something in front of it. That's nx to the n minus 1. Okay, Davon, what does the product rule say? Yeah, you got the worst one. I'm going to give you something else. Where's Mahir? Is he here? I don't think he's here. Okay, Mahir, you can, Carrie, you can give me Mahir's question, which is what is the derivative of e to the x in the natural log of x? What's the derivative of e to the x? Are you there? Go ahead.
The derivative of e to the x is e to the x
And natural log of x?
is 1 over x.
Thank you. You're done. Naina, what is the derivative of sine, cosine, and tangent? Derivative of sine is cosine. Derivative of cosine is minus sine. And the derivative of tangent? You need to look at that thing. Anyone have it open? Sarah, do you have it open? It's a derivative of tangent. Secant squared. It is secant squared. That one, I won't be embarrassed if you don't remember that one. Like if you go on to some future endeavor and you don't remember the derivative of tangent, that's not the end of the world. But sine and cosine, definitely you need to know them. I will not put that on formula sheet because you need to know them. It needs to flow from your lips. Derivative of sine is cosine, derivative of cosine is minus sine. Okay, Anusha, what does the chain rule say?
It says that you first have to do the derivative of like the outside function and then multiply it by the derivative of the inside one.
You're missing one part there. Derivative of the outside function, and what do you do to the inside function? You
Don't do anything.
leave it inside. So you have an inside function,
Right.
take the derivative of the outside function, you leave the inside alone, and then you take the derivative of the inside function. Yes.
Yeah, okay.
Great. Melanie, what's the relationship? Last time I only asked you to do the relationship between position and velocity, but you can almost tell me what the answer is to the next part. What's the relationship between position and velocity? The velocity is the what have you been doing all along? These are applications of what? Do you not know? Is it not listed in the answers? It isn't? I'm sure it's listed somewhere, it's just not on that one. What is this section? What are we talking about? What have we been talking about all along? Derivative. So position, you take the position is just like where you are. The velocity is going to be it's going to be the derivative. Okay. And just like we did with those just like we were just doing with those projects, remember there was the table, the function was just the value. Then the next thing on the table was the first derivative, and that was how quick you were going, like miles per hour. And then what was the last one? The last one, I kept saying was accelerating or decelerating. And what was that? It was a derivative with not one little prime, but two little primes, which means it's a what? Double derivative or second derivative. Yep. That's what we're doing today. Okay, so the relationship is that velocity is the first derivative and acceleration is the second derivative. All right, that's what we're doing though. All right, pretty good. I will take that. So here's the only one who's not here today. I just took attendance. All right. So let me take a look at my notes now. So let's take a look at the different topics that are covered here under implicit differentiation. There we go. So what is implicit differentiation? Okay, so velocity is the derivative of the instantaneous derivative. So velocity is another way of saying IRC, by the way. It doesn't say that. So there's my mother implying the guillotine. Implicit differentiation is that you are implying something. Okay, so explicit differentiation is when you have y equals f of x and you just want the derivative, right? Implicit is when you have the y in an equation. And the way what you're gonna do is to apply implicit differentiation, to apply it. You're going to take the derivative of the equation, both sides of the equation. Okay, and then you're going to be careful to use the chain rule when needed. Okay, and then solve for any derivatives. Okay, and there may be more than one correct answer. So remember, so here's what I mean by the chain rule. If you're taking the derivative of x squared, that's 2x. But if you're taking the derivative of y squared, and that derivative is with respect to x, then there's an inside function, then we're using the chain rule. Remember, you bring the 2 down, you subtract the power, and then multiply it by the derivative of the inside. So there's a y prime. So if you have an equation with a y in it, like for example, this equation right here, here's the equation of ellipse, 2x squared plus 3y squared equals 45. Okay. I don't know why it says that, but okay. 2x squared plus, I forgot what that was. What was it? 2x squared, 3y squared, and 45. There's an equation. And there it is. There's an ellipse right there. Are we good with that? Okay. So what we need to do is, what is the derivative? What's another word for the derivative? Sarah, one of the questions, you're the one. Sarah, no, you had the derivative of 0. Who had all the derivatives? What was one of them with the something of the something line? Slope of the tangent line. While this is not a function, you could see that it might have a tangent line. Okay. A tangent line could look something like, I don't know. Here's a tangent line right there. Okay. And to get that tangent line, you're going to have to know an x value and a y value, because this one right here is the same x value, but a different y value. Okay. So what happens? So what we're going to do is we have an equation and we're going to take the derivative, copy this, paste it. I'm just going to take the derivative of both sides. And the way I'm going to do it is I'm going to write dx. And I'm going to do, actually when I do both sides, that means I'm going to do every part. That one, and that one. Okay. Okay, so Jake, you had the power rule, right? What's the derivative of 2x squared? It's power rule. 4x. That's just 4x. Got it. Who had the chain rule one? Oh. I knew sure you had the chain rule. No, Suhabe had the chain rule one. What's the derivative of 3y squared?
6y?
Okay, let's just say that's right when it isn't.
Oh,
Let-
sorry.
Hold on. Does anyone know what it needs to be? Remember, I went over this before. I just sort of said when the variables don't match. So you have y squared, it's what? It's not just 2y, it's 2y times.
Y. The 2y times the, okay.
So if I don't put the y prime in, let me show you what happens when I don't put the y in there. Can you also, Sarah, you told me, what's the derivative of 45? It's a constant. Derivative of a constant.
Yeah.
Okay, if I do that, I have an x and a y, but I have nothing to solve. I have no derivative to solve for. I have to have the y prime in there. So I have something to solve for. Otherwise, I got nothing to solve for. Okay. Let's see. Then they say, find the, and they give you a 0.33 on the ellipse. So let's go back to our Desmos thing. So we know that x equals 3 and y equals 3. So I can just put 3's in here, right? I can put a 3 in there. And I can put a 3 in here. And now I have something to solve for, right? Okay. So this is 12. This is 3 times 6 is 18. Okay, I can bring the 12 to the other side. So I'll do it this way, minus 12. Are we good? And then I can take them 18, take it to the other side. Okay, that's the slope of the tangent line at a point, at the point 3,3. Okay, if I want to see that, I need to see, remember I can do y minus 3 equals minus 12 over 18 times x minus 3. Do you see it now? You see the tangent line? Are we good with that? Okay. Any questions on this? So I have the ellipses here, and at the point 3,3, I have that tangent line like that. And the slope of it is minus 12 over 18. That could be reduced too. Okay.
I do have a question.
Yes, Christian.
Does the ellipse happen because both the x is being squared and the y is being squared? Or does that have nothing to do with it?
Once we take the derivative, they're not being squared. But the one thing is the 0.33, one thing I have to do in making this problem is make sure that the 0.33 is actually on the ellipse. If I plug 3,3 into the original equation, then I'm doing some squaring. Okay. So if I go to the original equation here, and if I plug 3 in for that, I get 2 times 9. 2 times 9, right? If I plug in here, I get 3 times 9. 3 times 9. That's 27 and 18. Is that true? Is 27 and 18 45? It is. So that point is on the curve. Okay. If they'd only given you the x value of 3, they'd have to tell you the y because there's 2 different y values. There's another one down here where it's negative. 3 minus 3 is also on this curve somewhere. There was 3 minus 3 is there. Okay, did that answer your question, Christian?
Yes, thank you.
So, here's a nasty problem. So when you see something like this, you see a y mentioned in more than one spot, then it's implicit differentiation. And this particular problem, I'm just want to read it because I think it used to be in your homeworks. I might have taken it out because these are just awful. You take the y and you multiply both sides by y. So you have 7x plus 4 equals this, 2xy plus y cubed. Then you take the derivative of both sides of the equation. You see how they're both being taken the derivative of? And on the one side, you get 7. On the other side, you get, now here's where they're ugly. If you have 2xy, that is a product rule. It's an x and a y. So when you take the derivative of 2xy using the product rule, it's the first, just 2x, times the derivative of the second, which is y prime. And then you have the second, then you take the derivative of the second, which is y, and you multiply by the derivative of 2x, and you get 2y. Does everyone see that is a chain rule? Not chain rule, the product rule. There's no chain rule there. Because you're just literally taking the derivative of y. There's y, it isn't in anything. The next one, though, the derivative of y cubed, what, you see that's 3y squared times y prime. That's the chain rule. Okay, that's the one we just did before. The variables didn't match, the x and the y don't match, so you end up with a y prime at the end. Okay. Now what you have to do is bring the 2y to the other side. It's just algebra. Group these all together, you have a y prime, and then you can solve for y prime instead. Okay, in other words, this graph, if I were to put this, you know, I've never done this, but I'm going to do it right now. 7x plus 4 over y. Back to normal. I think that's it. Is that it? Was that what we were looking at? 2x plus y squared. 2x plus y. Yeah, there's a graph of it. Desmos, isn't that cool? Desmos does that graph. Is that a function? Why isn't it a function? It fails that vertical line test thing. I know, curses. Okay. But the derivative can be found on this. There's a tangent line pretty much everywhere. Although honestly, I think right here, the derivative would be, the tangent line would be vertical, and so it wouldn't be defined. Okay. Because the vertical line has no slope. Okay, so if you're asking the slope of a vertical line, there's no answer. But anyway, that's the function. And the derivative is the derivative of 7 minus. So if you tell me the x and y on the graph, I can tell you what the derivative is. So 7 minus, can I get this? 7 minus 2y all over 2x plus 3y squared. I don't remember what it was. 7. 2x plus 3y squared. So that would be the derivative. That there's no graph of that because you need to know what x and y are. It depends. But if I find a point on, if I find a point like right here, that's like 0 and 1.5. Let's go with 0 and 1.5. I could plug 0 in. I could take this thing. It's not a function, so I have to plug in 0 for x. So that would be 2 times 0. And I have to plug in 1.5 for y. Okay, before I finish this, is that answer going to be a positive number or a negative number? Is the slope of the tangent line right there? At that point, is it going to be positive or negative? Is the slope going to be positive or is it going to be negative? Positive. So let's just do that and make sure we get a positive answer. It is. It's not a very big number either. See, it's like 0.5 something. Let's try this point right here, the one that I said that doesn't work here. Minus 0.5141. Again, here's Decimus only giving me 4 decimal places. Just copy this. That's the X value, right? So that goes here. Okay, and then the Y value was what? This one. That's in for Y. Okay, plugging it in for Y, plugging it in for Y. And what did I get? Positive number, negative number right there. Negative, but small or big? Huge. If I had more decimal places, I'll bet you this would be 0. Or not 0, the denominator would be 0, it'd be undefined. Okay, that's the point. The vertical line is it's decreasing, but it's really, really steep. Okay. So what's you have to picture, can I show you what I mean with the annotate here? The tangent line here is almost vertical. And if it's vertical, it'll be undefined. Tangent line here is lame. Okay, I can't even draw it there, but it's there. Okay, it's very mild. See that? What do you think it would be there? Very big or very small? Yep, slope of that almost vertical line. Almost vertical. No, it's flat, it's 0. This is 0. This would be almost 0. Like these are over here, it's almost 0. Then it gets steeper, then it gets steeper, then it gets super steep. And then it gets super steep negative. Then it goes back to almost super steep, but then it's now super steep positive, and then it's flattening again. Okay. All right. This isn't a function though, so it's hard to picture it, but that's what it does. Any questions on that?
Yes, I do.
Okay, go ahead.
Okay, when you have a vertical line test that fails, would an academic, as far as like the law of mathematics, would an academic scholar tell you to disregard this as a functioning equation, or could it be used theoretically in some other cases, the real world applications?
Okay, so because it's not a function definitely doesn't mean it's not real. A circle is real. There's lots of real life applications of a circle. It's not a function. It just means I can't find the slope of the tangent line without knowing more. If I can't just say it's a function of x, I have to give both an x and a y value, just like I was doing here. You see how I plucked the x value off and I plucked the y value off. That's how I was able to find the slope of this tangent line right there.
Yes.
Okay. But this is so as far as implicit differentiation goes, it's not something you see every day. And honestly, in Calc 3, they'll have a better way of doing it where you don't have to do it. You don't have to have this nasty thing going on. But you're not going to see these things every day. So I wouldn't worry about it. In fact, I'm going to read the next example right here has a square root with a product in it and a chain rule. You can look over this. I'm not going to go over this. I'm sure I've removed this from your homework. I'll just take a look at your homework and see. Okay, but these used to be prescribed in the course, and now I'm losing interest in them. We use implicit differentiation for something useful. There is something we will use it for. But it won't be just find the derivative of this equation, because this equation is not happening in the world, at least in my lifetime, maybe in your lifetime, but these functions are just off the wall. So here's hyperbolic trig functions. So I told you about them already, so it's the next topic. So the SINH so here's the thing, since you have to say stuff in this class, SINH is not sin H, it's cinch. Like you would say the word you know, like the word cinch. Okay. And the COSH is cosh. Cinch and cosh. That's how you would say them. Or if you like, you could say hyperbolic sine and hyperbolic cosine, but you cannot say sine H. You understand? Sine H? No. You didn't have calculus if you say sine H. And you'll lose points, lots of them. Okay. They're defined to be this right here. If you ever need to know them, that's the definition of them. Okay. Now, cinch and cosh are the only ones that have words that you can say. The rest of them have to be said hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant. Do you see how they're those trig functions with the H at the end? That's what they are. Hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, etc. Okay. So now they're like trig functions. So they have identities. And this is the only identity that they use in Calc 3. That the hyperbolic cosine squared. You know how sine squared plus cosine squared equals 1? Well, hyperbolic trig functions have cosine squared, hyperbolic cosine squared, or cosh squared minus sinh squared equals 1. So there's a minus there, not a plus. So again, you had me for pre-calculus, you know, when your kid turns 1, you can either put the number 1 on your birthday cake, or you could literally write hyperbolic cosine squared plus hyperbolic sine squared. Happy birthday. Okay, happy hyperbolic cosine. Okay. Mine has a lot more than just 1, but anyway, there's other identities. Hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Hyperbolic cotangent is cosine of hyperbolic cosine over hyperbolic sine. Hyperbolic secant is 1 over hyperbolic cosine. Hyperbolic cosecant is 1 over sine. Just remember that these are like trig things, and that's why they use sine and cosine. They use those. They put that little h in, it's a whole different thing. It's a completely unrelated thing. So for example, of course, all you really need to know are the derivatives, but let me just go into Desmos for a second so you can see what they look like. So you can just say y equals sinh of x, and there it is. That's what it looks like. You know how sine is periodic and stuff? This has got none of that. Cosh. Let me just put it here. Cosh. That looks like a big old parabola. Hyperbolic tangent. I don't know what that looks like. Okay. Hyperbolic secant. So even though you don't look at that, these are just functions. They're just new functions. Will you use them? If you're going to build another model of the arch, you might use them. If you're taking Calc 3, you'll use them for conic sections and stuff. But again, you'll relearn it by then. So you won't see these in Calc 2. They're just more transcendental functions. What else do you need to know about these things? You need to know the following. You don't need to know the identity. I'm never asking you that. You don't need to know what to find. I'm not asking you any of these things, but I will ask you what's the derivative of the hyperbolic sine? What's the derivative of sinh? It says it right there. What is it? Cosh. What's the derivative of cosh? Sinh.
Sinh.
No, there's no minus sign here. So derivative of sinh is cosh, derivative of cosh is sinh. That's it. And then there's more, I don't care. There's the derivative, remember the derivative of tangent. Who was it who had to do the derivative of tangent? That was you, Nana. What was the derivative of tangent? Secant squared. So the derivative of hyperbolic tangent is hyperbolic secant. Okay, fine. All right. There's pictures of them, don't care. All right. So we're done with that. That's not literally, that's a question on the test that rears its head once in a while, just enough to jerk you around. Okay. I have to say that I covered it and I have to put it on your test, but it's really very easy. Okay, I will not ask you anything but sine or hyperbolic sine or hyperbolic cosine, never any of the other ones, so you can let them go. Yes, Dana, what do you want to know? Oh, the October 4th,
2 weeks, 1 week,
the first test is in,
next Thursday?
is it? Maybe.
No, it's Friday. Wait, I know next Monday's the 30th.
The 4th is next Friday. So we got 3 more classes for you to get all this stuff down. This is the end, this material is the end of that, though. Are you freaking out? It's just, you'll see. The first test is really just so you see what the test is like. If you want to freak out at the midterm, don't freak out at this. 15, three of each type. So there's 3 vocabularies. Those are usually pretty easy. There's 3. Say these out loud. They're pretty easy. Then there's 3, what happened here? Those are not so easy. Then there's 3, do these. Write this like solve a problem. And then there's 3 that are, use the data to draw conclusions. And you just told me those were easy, and they pretty much are. So the first 2 and the last one are easy. That's 60%. You can pass this without even knowing how to do a single problem. So try to know how to do some of the problems, though. Okay, Newton's method. Can I move on to Newton's method? Are we good with that? So I'm just telling you these exist. They're new functions. They're functions, though. They're not derivatives of what we know now, and they have derivatives because they have, they have inverses as well. Here. Remember this? If I put raised to the -1, that's the inverse hyperbolic. Okay. And maybe there's identities, maybe there aren't. I think that's a pretty cool function. I kind of like it. You don't see that every day. Okay. So I was used to, when I was younger, I used to make up, I used to like to make up things that were describing this. So that especially relationships. If this was a relationship, this is a relationship that started off really great, like you loved the person. And then it just went into the toilet. Okay. You actually lost interest in them pretty fast. And then you lingered in the relationship for a while. And then by the time you got to 1, you were done. Okay, 1 year and done. Guys don't have relationships. You don't think that way? All right, never mind. I always used to try to, that's how I would remember curves. I've lost my spot here. Okay. Okay, so what is Newton's method? Newton's method is a way, I told you it's a way of finding more decimal places. But when you're on Desmos, oh, thank you. When you're on Desmos, if you want to solve an equation, if you just type in x equals 4, I mean, just, oh, it's not on the screen. If you just look at this, x equals 4 is a vertical line. That's what the equation x equals, right? But if you put it in a more complicated thing, like 4x minus 2 or whatever, and we have to solve this, so you still just have the solution here if you want it. Right? So what I'm saying is we could always write an equation no matter what it is. If you want x squared equals 4, the answers are 2 and -2. Okay, but I could take that equals and put a minus, write it this way, equals 4, and I get the same answer, right? Okay, so Newton's method is a way of finding these zeros, but getting lots of decimal places. So if I have something like x cubed, like that, you see this? Oh, and by the way, now Desmos won't tell me the answer. But if you just take the equal 0 off, it graphs that cubic equation. And if you just, it always tells you the 0. But you see, it tells you the 0, but it only tells you 4 decimal places. So what if you want more decimal places? Okay, you use a method called Newton's method. Let me see if I can. Okay, let me go back to my notes and see, because it's written out. So if you want to solve x squared minus 4 equals 0, you start, so this is the process. You start with the guess. So you could say, I'm looking for the function equals 0. So you start with some guess, and they call it x sub 0. And then you create a tangent line at x0. And then you find the x-intercept of that tangent line. And then you let that be x1. And then you just repeat the process again and again. You find a tangent line at x1. And then you find the x0. So let me see if I have a picture of this. So here's the parabola. So we found a tangent line right here. And then we find the x-intercept. So this is the x-intercept, right? Where's my pen? So right here is the x-intercept. You see that? So here's the tangent line, and you find the x-intercept, and that becomes your new guess. So that's like -3 or something, -2.5. So now you create a tangent line at -2.5, and you find the x-intercept there, and you see the x-intercept is really close to the 0. This process could help you find the 0. You keep repeating it over and over again. So it's 2.05, and then you repeat it again and again, and you eventually get the answer. So this is interesting because this is the old calculator, and finding the 0, it used to be like, give it a left bound, give it a right bound, and then it would say, give me an initial guess. And then it would use Newton's method to find the 0. So we just repeat this process. So here it is on the calculator. You type in all of this, and this is what the calculator was doing. So you start with a guess. Here the guess is 1.5. And then you plug it into this equation, and eventually it comes down to 2. And when it stops changing, you have your answer. Okay? So where did that come from? So in Desmos, we can do the same thing. We can find the function, we can find the derivative, and those were all part of the tangent, like finding let me go back here for a second, hold on. When I find the x-intercept, or the x-intercept, that means y is 0.
Newton's method.
You can see, yes. Do you see how?
Newton, yep. Yeah, Newton. This is the physics.
Okay, so this is the derivative at x0. This is the function at x0, and this is x minus x0. This is the equation of a line, but all I'm doing is solving that x. So when I do that, I rearrange stuff, and I have x0 minus f of x0 divided by f prime of x0. Okay, so that's the process. So now that's the formula for Newton's method. So when I do it in Desmos, I say, okay, there's the function 2x squared minus 4, and the derivative is 2x. So if I take 1.5, which is the guess, and I subtract the function evaluated at 1.5 divided by the derivative evaluated at 1.5, I get this number. And then the next thing I do is replace all those 1.5s gets replaced with this number. And I get a different number. And I keep doing that. Okay, there's a warning here that you might have a bad guess, and you might just end up going back and forth and not settling on anything. Oh, wow. That image did not come out good. All right, so here's a problem with Newton's method. So let's try this. Oh, okay, not you. Pick this Desmos thing here. So we're trying to find the 0 for this equation. F of x equals x cubed plus 3x squared minus 1. There's the function, and we're going to find one of these. It says start with x0 equals 1. So it wants us to take 1 minus f of 1 divided by f prime of 1. Now, I don't even have to figure out what the derivative is. I can just leave it like that. Desmos will do it for us. Okay, and what do I get? 0.66667. I got it as a fraction. I'm gonna take that 2/3. So let me copy this again. Copy. Paste, and I'm gonna replace all those ones with the 2/3 that I got. Copy. So now this is the next guess, is let's try 2/3. And then I get this number. Okay, I'm gonna take this, I'm gonna copy it. Paste it. I'm gonna take this number right here. I'm gonna put that in for all of these. Paste. Oops. Let me make it bigger. Paste. Paste. Could you see how the number's close, but not the same? So I'm gonna take the same number. I'm gonna show you an easier way to do this in a second. Take this number, and I'm gonna put it in there. Paste. 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 And you see how it's there now, it's not disagreeing so much. So again, I'll take this number, put it down here. I'll take this number, copy it, paste, paste. And you see they're really close now, and they're close by how many decimal places? 0.5320888 or 889. That's good enough. Now we have more decimal places. So that answer right there is probably this one point. It's this one point. On Desmos, it's 0.53209. But the answer is really 0.5320889. Okay. 2, 4, 6. Actually, yeah, anyway, do you see what I'm saying about you get more decimal places? That's how you get more decimal places. There's an even easier way to do this. Yes, Dana. So zero. Yeah, the x-intercepts. Getting more decimal places. That means solving any equation, because you have any equation you want, like x greater equals 4, you just move the 4 over. You just take everything on one side and move it over, and what's left? 0. So that's why Newton's method is used for finding the zeros. It's really solving an equation. Okay, but I did the same process every time. So for Newton's method, I could do this. I could say z of x. So I'm creating a new function. I just take x minus f of x divided by f prime of x. That's a new function, right? So what happens if I do z of 1? Z of 1. I get that answer, right? Instead of typing all that out, I just have z of 1. That's pretty easy, right? What about this next one? I could do z of 2/3 then. Hold on. Z of 2/3. Get the same answer, right? Oh, but even better. Where did 2/3 come from? That was z of 1, right? So what about this one? Now I want to plug that number in. All I have to do is keep putting z's in front of this. Z, Z, Z. Oh, Z, not Z. No. You see how it just keeps saying Z of Z, and eventually I get the answer. So I don't even have to do all that copying and pasting. I just have to create this function Z. I create this function Z. And by the way, this formula is given to you on the formula sheet, but not the function. If you create the function Z out of that formula, you just put the guess in, whatever guess they tell you to put in there, just put it in Z of 1. That gives you whatever their guess is. Suppose they want the other answer, Z of -5. Okay, I can just put -5 in here and I'll get the answer. So that's another 0, -2.879. That must be this one here. -2.87939. -2.87939. 079158. Okay, so you see how you can use Newton method to get more decimal places, but to do the Z thing, and it goes much faster than copying and pasting. I just would understand that this Newton's method was used by programmers to answer this, to get more decimal places. Like that's what they did. To find the zero of an equation, to solve an equation, to do what that old calculator thing did there. This old calculator, dust off your old calculator stuff. This was all done. This was programmed into Newton's method to find the zero. If you clicked on find the zero of an equation in your calculator, it was using Newton's method. So it's historically interesting, but actually kind of boring. Here's another one. I took this because this question's horrible. Use Newton's method to approximate the cubed root of 18. Well, you could change the cubed root of 18. You could say x equals cubed root of 18, x cubed equals 18, x cubed minus 18. So you want to solve the zero of that. Okay, and then you could use Newton's method for the function you're going to use this x cubed minus 18. And the derivative would be that. And then you could just put it in, check it, or you could use that z thing. Honestly, I'm not going to answer you that question because what would you do instead of that? This cube root of 18. Fine. What's the cube root of 18? Anybody? 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 How would you get it? Okay, so here if I use Newton's method, I get the cube root x cubed minus 18. Okay? And I can put in, go back to where I have all these z's. It says 2.3, right? I have to put a different guess in. 3. I still get a lot of decimal places. 2.60, whatever. Let me do some more z's. See, whatever. Anyway, there we go. That's the answer. But really, you want the cube root of 18? How would you get the cube root of 18 if you needed to get it on a calculator or on Desmos? $18 raised to what? Well, not the third. Cube root. Did I need to use Newton's method to get that answer? I got the exact same answer, but did I? No. All right. So Newton's method is not exciting for that particular question because you could do it that way. Or you could actually even get the, I'm sure there's a cubed root button here, isn't there? Is cubed root one of the things? Nth root. What's it in? Anyway, are we okay with that? So that's all I have to do. So those are the big, we just learned some applications of derivatives and a new function. We learned the hyperbolics. We learned implicit differentiation. We learned Newton's method. Okay, next time we have more to do. But I'm going to break us up into our groups now because I've been rambling on for a while. But next time we're going to do position, velocity, acceleration, and higher order derivatives. Okay, so what are we doing now in our groups? We're moving on to transcendentals, right? Discussion transcendentals. Writers can speak to, yes. Okay. This is differentiation. I did the implicit differentiation stuff. I did the hyperbolic functions. Newton's method. We did. Oh yeah, see there. I did the Z thing. Higher order derivatives are just first derivative done twice would be the second derivative, third derivative, fourth derivative. Do more of those next time. Oh, higher order derivatives after 3 dashes, 3 primes, you have to put a little 4 and a 5 in parentheses. That's not the, if you want the function raised to the 4th power, you don't put the parentheses in there. See parentheses around a number, that means a derivative. Okay. Acceleration is derivative of velocity. Okay. So let's do our group work stuff. What's our group work stuff? Mod 4 is open now. So if you go into Mod 4, you will not see what you're looking for. Where's the, there it is, discussions. So for some reason, it's at the bottom here and it's not a harmonized yet. So give me a moment. All right, so what are you gonna do with your example worksheet? Or with your worksheet? You go to transcendental derivative. Okay, transcendental functions. So I picked one for you. Okay, you could pick any function you want for transcendentals. You could pick hyperbolic sine. You know how easy it is to pick hyperbolic sine? I just put in H there. Now it's hyperbolic sine. I don't want to do that. I want to pick the sine. And it's already set up in such a way that the period is going to be this number that's down here. Okay, or right. So the period is given in this, I think it's, you have to double check it. So I think I had to change it, it was wrong. So this says the period is 80. So if I graph this, does that look like a period of 80? Period is how long it takes to repeat. Here's 0. When are you back at 0 again, going up? Here you're at 0, but you're going down. Here you're at 0 going up, right? That does not, yeah. So is that 80? 79? Close enough. It is 80. So yes, the period is 80 here. So that number is correct. If you have a 4 and a B1 minus A1, then that's correct. If it isn't, be careful, because on the test, I think one of quizzes, sometimes the formula is wrong. But just double check by looking at the graph and make sure. So there's the period. So you have to mention the period because you can change the period. This sine function, let me just put the data on for a second. Here's the data. Okay, I picked this green. So the data goes up like that. The quartic goes off to infinity, but the green one goes up and down, which in my trip to Florida might actually make sense. I go to Florida, I come back. I go to Florida, I come back. The distance is going, you know what I'm saying? I'm going to Florida and I'm coming back. And if I do that every 80 hours, then yeah, it takes 80 hours to go to Florida and come back. It doesn't take 80 hours. What if you said it took, how many hours does it take to go to Florida? No, you can change this so that the period is smaller. If I change this B1 to 10, what's the period going to be? Period is now 40. So that's 40 hours. That makes more sense. Driving to Florida and coming back, 20 hours. If I could drive continuously without stopping, it would be 20 hours there and 20 hours back and 20 hours there. Back. See why that could be this has a period of 40. Goes from bottom to bottom. Anyway, how fast was I going at the 12th hour? How fast? Well, where was I? Between here and 1,000 miles to Florida, where was I? So according to the sine regression with a period of 40, in the 12th hour, I was where? Somebody say something. Just say it off the graph. The 12th hour, I was at what mile marker? 703. How fast was I traveling? 15. That's not bad speed. And was I accelerating or decelerating at the time? I was slowing down, probably cops. It's probably only 55. Okay. Where was I? Pick a time, another time. So I for this new job where I drive to Florida and I drive back. That's all I do. Florida back, Florida back, Florida back. Give me a time. Anytime. No, hours.
Oh,
If I leave at midnight, that would be 8. So where am I at 8 a.m.? I've left the house I left the house at midnight. And at 8 a.m. where am I? Somewhere around North Carolina, I would say, halfway, 443 miles. Okay, how fast am I traveling? How fast am I traveling? At 8 o'clock in the morning. Come on. Fast am I traveling? We just did this function. Nope, that's where I am.
Oh, 66.
67 miles per hour. And am I speeding up or slowing down? I'm accelerating. Must have just passed the car. Okay. Do you see how you read that? So you just have to say, just don't leave this as A1 and B1. But in order to change the period, I'm not sure if I give you an option on your worksheet, I might have, let's see. Your worksheet, the blank worksheet might have something else on it. Transcendental derivative. C1 is the period. No, it's just whatever that is. Okay, so you can change you can change A1 and B1 to different values to change the period. So let me see again. Let me just show you that one more time. I'm gonna go back here. So I can't change both of them, but do you see how the regression looks? Actually, the sign regression doesn't look bad here. The green and the purple are kind of close. Not really close, but kind of close. Okay. So let me just say, look what happens if I change the regression. I change the B value. I change the period. That maybe, how about that? That's not bad. Okay, so change one of these so that it looks pretty good. And then take off the, I don't want this function I want off. Why is that purple function on at all? Where is it? Let's see. Okay, does that look bad? So now I got the data and I have a sign regression, and I want to say the same things I said last week with derivatives and stuff. Okay, and if you're doing the table, you're the producer, make sure you do a table and pick different values. Okay. And then the writer does the same thing you did last time, and then the speaker does the same thing, except the speaker has to mention the period because you are allowed to change it. You can pick whatever period you want. Okay. And then if you have time, you can move on to mean value theorem if you want. I think I discussed this last time. That's just a matter of turning all of this off, turning back on the quartic regression. And then all you have to do is click this one on and click that one on and look for the intersection. And then plug it into the table. Or plug it into these functions to show that the average rate of change is equal to the instantaneous. Say the average rate of change is 50, the instantaneous rate of change is. And again, I showed you last time with all these extra decimal places that Desmos is giving us 52975. I get even closer to 50. When I had those decimal places, Desmos only gave me 3 decimal places. When I created this, now it's giving 5. All right, so you have 2 things. Let's get into our groups now. Okay. Does everyone know what group you're in? I have some people at home. How many groups do we have in this class? Just 2? Okay, the business people were in group 1. The business people were the ones that had the BFFs. So BFF people were, okay, Anusha. You guys are you guys are all in the same group? Are any of these people in your group? Kara's not in your group. Suhabi's not in your group. Anusha's not in your group. Really? So they're all home and you're all here. That's just weird. All right. There you go. Christian, the only group that's active is room 1. So why don't you go in there and hang out with them? There you go. What? You guys really all the same? You're all here?
Professor, you didn't sign it up.
What assignment? Oh, it's gone up. You need it up, right? Hold on. I have it up for the other class. I just don't have it up for you. Hold on, let me see. Transcendentals. Okay, it should be up now. Right there. Okay, hold on, I'm gonna move some things around. Yeah. It's really quiet, so I'm gonna just join that group. So it's just stop live. It's still live streaming. Okay, so I'm gonna put it in the chat, Javon. So you're gonna see it right here. Okay, that's a YouTube thing. See if it works. It should be a little bit behind. But once it's there, when I hit stop the live stream, the video will automatically be up. It's not working. Did you get it? I clicked on it. It took me here. Did it come here? It looks exactly like this. Is there a playlist? These are all the playlists. Do you see one that says? No. Is there one that says live stream? Yeah, so where's my live stream thing? Or live? Oh, click on the live thing. Does it have that? That looks like what I'm wearing today. Maybe not. Wait, is that red or blue? This is an old one. Huh. Well, that's not it. Live is there. It's recording somewhere, right? I mean, it took you to my playlists. So it's got to be here. It can't be anywhere else. Where is it? This was 6 days ago when I got it to work. Because I got it to work on Wednesday. So this one I don't want anymore. So let me just delete that. No. Wait. Oh. Did it say save to share? No. Add to queue. No. My channels.
Step that.
Like this one?
The hell am I listening to? Oh, sorry. So I couldn't find that video. I don't know where it was. That certainly got it to stop doing that. Okay, so I'm in my YouTube channel. This is your channel. Manage videos. Live. There's one live right there. Why can't you see it? It's unlisted. So make it public. Is that the problem? Okay, so now see if you can see it. That's right. And where was it? Streaming software. It's live now. Okay, let's do this one, make it private. So now you can't see those, but you can see the one that's public. Okay. Is it working? I mean, it's live right now. If you click on it, you can see what's going on right now. Good. Okay, cool. All right, I'm shutting down the breakout rooms. Thank you for helping me with that, Javon. Okay, so. Yeah, Nusha, can you hear me?
Yes, I can.
Okay, good. So let me just finish this one thing. I wanted to show you that the live stream works. We've tested it. See, I can never test any of that for me at home. So if you want to see the live stream, it's on my YouTube. I'll post it. I'll post a link if you want to see a recording of today's lecture. But anyway, these are the homework. This is homework 4. You'll notice we did this implicit differentiation. You know, there's this one, and then there's this one. These are all implicit differentiations. Then here's a Newton's method. Again, you could do that Z thing to do Newton's method. This is another Newton's method. You could do that one. Here's another Newton's method. All right. Question 8 is given the height of compute the velocity and acceleration. So if this is h, what's the velocity? Is going to just be the first derivative, and acceleration is going to be the second derivative. And that's really easy to do. Another one, first derivative. This one, you could find the acceleration. That's just, it goes right to the second derivative, no first derivative. So the only thing we have to do, oh, and there's 2. So you can do question 11, which is the derivative of hyperbolic sine squared. And then there's this one's the fourth derivative. I will talk about them next time. Bye. Are we good, Kara and Yusha and Javi? Okay. Have a good one. Feel better, Kara.
So
Bye,
I
have a good one.
made this like a post, as in like one of these by accident. I made my answer that instead of putting it under someone
Put
else.
it with reply.
Yeah, I made it a different.
So
post. Could you
copy it.
just
copy it?
Yeah, I was
and
gonna
then
copy it, but
put
I
it-
just wanted to make sure.
Yeah, I can delete it. Sure.
All right.
Do you want me to delete it now?
Uh,
Copy it and paste it
yeah, I'm
into an
trying to
answer
copy it.
before I delete it. But yes, I'm going to stop live streaming. So that's kind of cool. Wait, I have to find out how to stop live streaming. How do I do that? So Zoom. Is anybody in Zoom? Okay, so here.